dies or a bird dies, anything dies, the level of carbon-14 starts to diminish out, okay? And it decays and it has a half-life, all right? I don't recall exactly, I think it's 14,000 years, but I'll get it exactly. Carbon-14 half-life. Oh, 5,000. Why did I think 14,000? 5,730 years is the half-life of carbon-14. So the way this works is that an archaeologist will go, dig up some place in some part of the world and they'll find a bone and they'll take it to the lab and they'll drill out some of the bone fragment and they'll test the carbon-14 and they'll measure how much carbon-14 is there. And they know, well, the gas tank was supposed to be full, but now the gas tank is only 20% full. And then what they have basically at that point is what we had with the Advil. We had, okay, you start with 800 milligrams, you end with 5, how much time went by, right? So they measure the carbon-14 when they find the bone. They know that at the beginning it should have been 100%, and then they can date the bone. They can figure out how old it is. Does that make sense? Yes? Yes. Okay. So let's do this. Let's just first answer one question. What is the master formula for carbon-14 dating? What is the exponential formula that is used for this? Okay? That's the first question. So find the exponential formula for carbon-14. Okay, that's our first question. Now to do this, you're going to help me. Start out with the formula that's used for all half-lives, which is this one. And how did we go about getting this K again for the last problem? What did we do? This step, this is a critical step to be able to get K. Okay, so how? Yeah. I gave you the half-life. I'm telling you the half-life. Yeah, so I'm giving this to you. Look, this is exactly the way a problem could appear on the final, okay? So we want to make sure we understand this. I will give you the half-life of something. You are going to have to come up with a formula for it. And then you'll have to answer a few more questions. Okay, so all we have is the half-life, and we have this formula. So we first go about finding K. Once we have K, then we can work with that formula and answer any other questions. So to get K, what do we know at time equals 0? How much is there at time equals 0? P sub 0, always, right? How much is there at time is 5,730? Half of it, right? This will always be the first steps to finding K, is just to understand that at time is 0, we should have that. But as time is, that time is 5,730, then this should spit out 1/2 of what we started with. So now, working with this, what should my next line be? We plug in, so I'm going to rewrite this. What is it? Half? Okay, P sub 0 equals? Just P sub 0. Yes. And then E? K 1,730. Okay? Every time you do one of these problems, after you've done this step, the P sub 0s will cancel. You will divide P sub 0 out on both sides, every single time. And the left side will be 1/2. The right side will be E to the 5,730K. And then what is our next step here?
Then we plug in the log.
that we get the log now, okay? So now we take the log on both sides. This will drop out in front. So we'll have natural log of 1/2 equals 5730K. And is there anything else over on the right-hand side with the 5730K? No. Why? What happened to the natural log of E? That's 1, right? What's next? Yeah, figure this out, right? Let's figure this out on our calculator. Natural log of 1/2. Negative 0.06931 equals 5730K. And now divide both sides by 5730. And you get your K. Now notice on this one, this K is, you're going to have to go a lot more decimal places. I don't want you to just use 1. I want you to at least get a few digits. This is what I got. Anyone else get something close to that? I got 0.0012096. Okay, so just use all the digits because for this carbon-14, you're going to have to go pretty far. Yes? Okay. So now we have K, right? Once we have K, we come back to our master formula right here, and we replace K, and now we can answer any question that anyone asks us about carbon-14. So I'm going to rewrite this. I'm going to put it up here. We have P equals P sub 0, E to the negative 0.0001296 T, and that is the formula I will use for carbon-14. Now on the review that I gave you for the final, right? On the review I sent in an email today, I gave the students the formula. And the reason why is because that particular class, we did not have enough time to go through this. So I just said, hey, if I give you a formula, can you figure this out? Here, because we had the entire day, I could actually go through and show you how you can come up with the formula yourself, all right? So unfortunately for you, you got to do this step. Okay?
Is there
Yes.
like a constant number for the carbon-14 amount that's in some creature's body? Like, because we say this amount was like, okay, half-life is half of whatever
Yes.
there was
Uh-huh.
before, right? And then it goes on, half of that half again takes this much amount of time. It just goes on, right? Like that?
Yes.
Half of half.
Mhm.
And at the end of the day, that's how they calculate the amount, like the year, how old that
Yes.
that voice or bone is.
Mhm.
So, but each time we go half, it gets smaller and
Yes.
smaller amount. So the time should the time be the same for that same, different.
Yes. Even though the amount's less, it still takes the same amount of time for half of it to go away.
It doesn't matter.
Doesn't matter how much was there to start with.
Say 20 pounds.
20 pounds.
Have 10 pounds. So the same time would take to break.
From 20 to 10 is the same amount of time it takes to go from 10 to 5. That's what makes half-life different from, and this is why you need an exponential model and you can't use anything like a quadratic or a linear model. A linear model would be like 20, right? And then maybe it takes a year for 10, right? And then a year later it's gone. Because each year is 10, right? That's not what's happening with half-lives. Half and half and half and half and half forever. And you'll never actually have it all go away.
Yeah, that's why probably they say, oh, this bone is some 3 million years.
Yeah. Yeah. Well, we're going to do that right now. So the way they do is they take a sample they take a sample of the bone and they put it like through a centrifuge, and then they measure the carbon-14, and there should be a certain concentration. Think of it as like salt water. You know, if you were to get a cup of water and just sprinkle some salt, well, get some water, taste it, there's no salt in it, right? You sprinkle a little bit, you're gonna stir it up, you're gonna taste it, right? If you put like a bunch of salt in there, it's gonna be stronger concentration. That's what they're doing. They're testing the bone and they're saying, what is the concentration of carbon-14? Is it strong? If it's strong, then it recently died. If it's very minimal, then it's old. So they measure how much is there. Does that make sense? The concentration. Oops, sorry. Let me turn this off. Okay. All right, so you ready? We now have a formula that we can use for carbon-14. Let's actually do a problem, all right? Like an age problem, all right? A bone is found and tested the bone contains .315% carbon-14. How old is it? So it's kind of like they tested the bone like salt, right? Said, oh, look at this concentration, just a little bit of carbon-14 in here. Very small percentage of it is carbon-14. So from that, can we determine how much, right? How old the bone is, sorry, not how much is there. All right, so here's our formula. So the tricky part of this right now, it's not really tricky until, you know, after I tell you, you'll understand it. How much was there to start? What is the starting amount for carbon-14? Yes, as a percentage, how much carbon-14 should be there to start? This would be like right at the moment the thing died. You should have all your carbon-14. You should have the full concentration, right? 100%. 100%. So P sub 0 is 100%, right? Agreed? Now, as a decimal, what is that? What's 100% as a decimal? Decimal point, move it over 1, 2. It's 1, isn't it? 1 is 100%. So here's what our formula looks like. P equals 1, right? I'm not going to write the 1. E to the negative 0.000120996t, right? We want to know how much time it takes for our final concentration to be what? This right here, right? So for us, P is going to be 0.315%. But what is that as a decimal? Be careful on that. As a decimal, what is that? 0.00315, right? So that means we're going to replace this P with this number. So we get 0.00315 equals E to the negative 0.00012096t. And just to recap, this is our original formula. We have to know the starting amount and the ending amount, and then this would be the time it takes for it to go from the starting to the ending. Our starting amount was what? 100%, so there's a 1 here. Our ending amount was 0.315%, so we converted it to a decimal. And now the only thing we have left to solve for is time. I'll see that? So what step would be next? Log. So you have to do natural log of 0.00315 equals, now what's going to happen on the right-hand side? I take the natural log, right? I drop the thing out, and the natural log of e is going to become 1. Right? So I'm going to take natural, I'll write it out. I'm going to do natural log on this side. Okay, this is going to drop. The natural log of e is going to go away. On our calculators, we'll do the left side. You should get negative 5.76035. I'm going to go like 5 or 6 decimal places. Equals 0.000120960. Understand that step? And now divide both sides by what? Oops.
That's not what
For what?
Oh,
The-
you know what? I added more zeros in.
Does anyone have an answer yet?
Is it 47621?
47621, and let's just leave it at that because this is an approximation. All right? This is years. – 47,621-year-old bone. Okay? All right. So, on the final, on Wednesday, I'm going to give you a substance. I'm going to give you its half-life. I'm going to ask you to come up with the master formula for it, and then I'm going to ask you 1 or 2 questions after that. All right? All right. We're going to take a quick break, and then we can come back. I mean, you have the review for the final at this point, right? You have the review I gave you last week. You have the review that I sent out today, right? So you have 2 reviews to go over. At this point, if you're happy and comfortable and think you're ready to come in on Wednesday and take the test with what I've given you, you're free to go. If not, we'll reconvene in about 10 minutes, let's say 15 minutes, take a little break. At 12:40, we'll come back in here. I'll answer any questions. I'll go over any problems you might want me to go over on the review. Okay? Any questions?
It was, no.
No? Okay, so 12:40, we come back. If you want to. Okay, so if you leave, I'm not going to be upset. I'm not going to count you absent or anything like that. But I want to make sure you